So we thank Yuri Nikonorov for his final lecture here on homogeneous spaces. And this time we'll talk about Ricci curvature for the final part.
Okay, thank you very much. Okay, our final part is devoted to the Ricci curvature and some related problems. I tried to explain some very well-known problem and some maybe not so well-known. But in any case, I think it's that problem are interesting. Okay, the most general setup. Let's consider homogeneous space G mod H with compact H. And non-formally, we are interested in the following question. What kind of invariant, this means G invariant, Riemannian metric, does this space admit? What kind of? Of course, we may focus on some natural characterization of invariant metrics that can retain several values in general, some numerical values, and try to classify all realizable values on given homogeneous space. There are a lot of well-known results of such kind. For instance, Riemannian homogeneous manifold with negative Ricci curvature is non-compact by well-known Bochner's theory. Okay, and something look like this. Here we can see some results related to the Ricci curvature. For a given invariant metric on homogeneous space G mod H, we consider the signature of the Ricci curvature. These three natural numbers N, Z, and P. That's a triple of number where N is a quantity of negative, Z is quantity of zeros, and P is a quantity of positive eigenvalues of the Ricci form, or by another term, of the Ricci operator, of the metric under consideration. Okay, that's then we can emphasize our non-formal question as follows. What triples N, Z, P could be realized as signatures of the Ricci form of some invariant Riemannian matrix on a given homogeneous space G mod H? What triple could be realized? Okay, that's very natural setup to my mind. And we have some very well-known partial results, of course. By the well-known result by Milner for Lie groups and Berestowski in general case, a homogeneous space G mod H admits a G invariant metric with positive Ricci curvature if and only if it is compact and has a finite fundamental group. It's criterion. If it's compact and has a finite fundamental group. Therefore, we have complete answer for this partial signature. Okay. Unfortunately, we have none of this result for negative Ricci curvature and for other possible signature. But in any case, there are some partial, quite interesting results that we discussed below. Okay. Okay, in what follow, we deal only with Lie groups G, ignoring our result on more general homogeneous spaces, because even for Lie groups, this result not so simple, not so obvious. Okay, the Ricci curvature of left invariant metric on a Lie group G can be entirely computed from the algebraic data. The structure of the Lie algebra G of G, capital G, and the inner product Q on this Lie algebra. With a slight abuse of terminology, we can speak yes, of the Ricci curvature of the metric Lie algebra GQ. As noted before, the signature of the Ricci curvature of left invariant matrix on three-dimensional group was classified by Milner. Some refinement of this result was obtained by Chebarikov and Huntley in corresponding papers. And what about four-dimensional case? The signatures of the Ricci curvature of left invariant metric on four-dimensional Lie groups was classified in two papers by Kremlov, this is my students, and Nikonorov. It should be noted that some partial results in this direction was also obtained in paper by Chen. But for dimensions greater or equal 5, we have various partial results, but not general. Not general result for even for n5. It's necessary to mention the paper by Isabel Dotti Miatella, where Ricci signature of left invariant remaining metric on two-step solvable in a model Lie group are determined. And the paper by Kremlov, where he determined all possible signature of Ricci operator for left invariant metric on nilpotent five-dimensional group, only five-dimensional. That's a partial result, but quite interesting. And recall also the following result by Kaiser, quite special. Each left invariant remaining metric on n-dimensional Lie group G with, it's very important, with a one-dimensional commutator group, possesses only signature n z p of the Ricci form with p is 1, n is 2m, where m could be of this type, if the group G is unimodular, and with p1 and 2 or p0 and 2 if G is non-unimodular. Therefore, in this quite partial case of Lie group, we have complete answer. What kind of signature could be realized as the signature of Ricci operators? All the signature are accessible. That is, there exists one of the above mentioned group which admits a left invariant metric with such prescribed signature of the Ricci form. Note that one of important tools in the above mentioned research was the possibility to choose so-called a good basis for computation of the Ricci curvature. Details of this technical problem one can find in these papers. You can consider it yourself and reference therein. It's quite difficult problem, but we have no serious approach without this. A good basis allows to compute Ricci curvature, allow to estimate some eigenvalues and so on and so on and so on. Okay. The above results lead to various conjectures. We consider one of them. It was shown in the paper, that the scalar curvature, Milner and Jensen, that the scalar curvature of every non-flat left invariant Riemannian matrix on a given solvable Lie group is negative. Therefore, the Ricci operator of this metric has at least one negative eigenvalue. Okay, since the scalar curvature is a trace of the Ricci operator, and this trace is negative, then at least one eigenvalue of Ricci operator should be negative. Okay, it's clear. Now, let's consider some formal thing. Let G mod H and G is a remaining homogeneous space with a reductive decomposition. The Ricci operator Ricci is defined by this formula. This is a Ricci form of the metric under consideration, and is related to this matrix with with yes, it's related with this metric by multiplying by some positively definite symmetric operator. This operator is called Ricci operator. Okay, and now we will discuss eigenvalues for this operator. Okay, the next slide. Various examples of solvable metrically algebras are such that the Ricci operator has at least two negative eigenvalues. The authors of this paper proved, it's our paper with my student Kremlov, proved in particular that the Ricci operator on every non-unimodular solvable metrically algebra of dimension less or equal 4 has at least two negative eigenvalues. Moreover, author of this paper posed the following conjecture. The Ricci operator of every solvable non-unimodular metrically algebra has at least two negative eigenvalues. Okay, this is not obvious, but naturally to pose this conjecture after consideration of many examples in dimension 3, 4. This conjecture was confirmed for all non-unimodular solvable metrically algebra of dimension less or equal by 6 by Chebarikov, it's also my students, for all completely solvable algebra in our joint paper with Chebarikov. Completely solvable means that the eigenvalue of all joint operator are real. Yes, it's very special subclass of solvable Lie algebra. And for all Lie algebra with 6-dimensional two-step nilpotent derived algebras by Abiev. And finally, this conjecture was completely confirmed in the paper, in my paper, as a corollary of more general result, which will be discussed below. As usual, we denote by bracket S, comma S, the derived algebra of Lie algebra S. For every solvable Lie algebra S, this bracket is a nilpotent ideal of S, and it is distinct from S. Recall that an operator A, any operator A, acting on given Euclidean space is called normal if it commutes with its adjoint A prime. We need this for statement of main theorem. And this theorem. Okay, let SQ be solvable metrically algebra, any arbitrary solvable metrically algebra, and is a derived subalgebra of S, comma S, A, B, Q orthogonal complement to N in S, then one of the following mutually exclusive assertions holds. The first one, the ideal N is commutative, A is commutative subalgebra of S, and for every X from A, the operator at X restricted to N is Q-symmetric with respect to Q. In this case, the Ricci operator is 0. The second variant, the ideal N is commutative, as in previous case. A is commutative subalgebra of S, and for every X from A, the operator at X restricted to N is trace-free and normal with respect to Q, but the subspace of Q-symmetric operators of this kind has codimension 1 in A. Not all are Q-symmetrics. In this case, the Ricci operator of SQ has only one negative eigenvalue, while all other eigenvalues are 0. And the third possibility, the third variant, the Ricci operator of the metrically algebra SQ has at least two negative eigenvalues. Hence, we see that the first and second type are very restrictive, very restrictive. Since we have several corollaries from this general theorem. For example, the cases 1 and 2 in this theorem are impossible for non-unimodularly algebras. It's easy to check that it's impossible. Because for non-unimodularly algebra, there is some vector that at x is not trace-free. It's definition of non-unimodularly algebra. Hence, we immediately get a confirmation of the above mentioned conjecture. Let S be non-unimodular solvable algebra, then for every inner product U on S, the Ricci operator of metrically algebra SQ has at least two negative eigenvalues. Moreover, we easily get also the following two corollaries. The first one is the Ricci operator of solvable metrically algebra SQ has at least one positive eigenvalue, then it has at least two negative eigenvalues. And the second one, let SQ be solvable metrically algebra such that a Q orthogonal complement A to N is the commutative subalgebra of S, then the Ricci operator of this metrically algebra has at least two negative eigenvalues. Hence, it's quite usual thing to have two negative eigenvalues, at least two negative eigenvalues. And also, we get the following result that was obtained earlier using other ideas in the paper myself with Chebarikov. Let S be a non-commutative nilpotently algebra. Then for every inner product Q on S, the Ricci operators corresponding metrically algebra has at least two negative eigenvalues. Therefore, it's a general situation for nilpotently algebra, not non-commutative nilpotently algebra. But in any case, the following open question is natural. Okay, which solvable metrically algebras have exactly two negative eigenvalues of the Ricci operator? In fact, I don't know what approach can help in solution of this problem. And it's quite interesting because this class should be restrictive, but I don't know how to get the complete picture for this class. In fact, we have some necessary conditions, some sufficient condition, but not general result. Okay. Now we'll discuss the following question. Which solvable Lie group admits a left invariant metric of negative Ricci curvature? By the following result, no unimodular solvable Lie group, in particular non-nilpotent group, admits left invariant metric with negative Ricci curvature. The theorem of Dotti-Meatella. Any left invariant metric with Ricci with non-positive Ricci curvature on solvable unimodular Lie groups is Ricci flat. It's very serious restriction. Further, it was proved that an unimodular Lie group which admits a left invariant metric with negative Ricci curvature is non-compact and semi-simple. Example of such metric was considered on the group of type SL-NR. And this result was extended to some other complex simple Lie group in another paper. Therefore, we have some solvable example with negative Ricci curvature and some semi-simple examples. It's strange a little, but it could be verified by direct computations. Okay. Let's consider the following theorem, which gives some necessary condition and some sufficient conditions for existence of an inner product of negative Ricci curvature on solvable Lie algebra. This results from our paper with Yuri Nikolaevsky. Suppose G is a solvable Lie algebra. Let N be nil radical of G and that B is the center of N. Then the first. If G admits an inner product of negative Ricci curvature, then there exists Y from G such that trace of a joint operator at Y is positive, and all the eigenvalues of the restriction of this joint operator to Z have positive real part. Okay, and the second, if there exists Y from G such that all the eigenvalues of the restriction of a joint operator to N have positive real part, then G admits an inner product of negative Ricci curvature. Of course, okay, we see that the difference is between restriction to Z, is the center of N, or restriction to whole N. But it's this condition give us necessary and sufficient condition in the case when the center of N is N itself. Therefore, we have immediate consequence of the above theorem. A solvable Lie algebra G with an abelian nil radical N, in this case, center of N is the same as N, admits an inner product of negative Ricci curvature if and only if there exists Y from G such that all eigenvalues of the restriction of the joint operator to N have positive real part. Okay, in this partial case, we have deuterium. And note that the latter property of G is equivalent to the following one. There exists Y prime in G such that the restriction of the joint operator of this vector to N is a stable linear operator, that is, all its eigenvalues have negative real parts. It's obvious, we can take minus Y from this theorem with this property. And in the same paper, the author also obtained necessary and sufficient conditions of the existence of left invariant metric of strictly negative Ricci curvature for Lie group with the nil radical of whose algebra is either abelian or Heisenberg or standard filiform. In the recent paper by Nikolaevsky, analogous results, analogous necessary and sufficient conditions were found for Lie groups with nil radical of whose Lie algebra is filiform. It's more or less general result, but for some special type of solvable Lie algebra, of course. And something more, in the paper by Ngaha, Bessetta, and Kamgar, they obtained some interesting result on the signature of the Ricci curvature of left invariant metric on more or less general nilpotent Lie group of large dimensions. But unexpectedly, on the other hand, the most general result of nilpotent Lie groups was obtained recently by Roy and Lafuente using the study of closed orbit and Saturn representation of the general linear groups. This is a theorem, the main result. I try to explain what does this mean. Okay. The set of signatures of the Ricci curvature of left invariant matrix on a connected nilpotent Lie group N, capital N, with Lie algebra N is given by, you see this union of some type of signatures N, Z, P, which described by some inequalities. Some inequalities with some parameters where we find, this, for example, these values, which are described through the dimension of n, dimensional of Zn, dimensional of commutator n with itself, and some more general construction. Okay, there are some special numbers which could be calculated explicitly for every given Lie algebra. And after we can calculate this, we obtain all possible signature of Ricci curvature of left invariant matrix. It's very, very general result. And this result solves the problem of find all possible signature for class of nilpotent Lie group and nilpotent Lie algebra. It's very nice. Moreover, in this recent paper by Cynthia Weil, she constructed many examples of solvable and non-solvable Lie groups that admits left invariant Riemannian matrices negative Ricci curvature. Let us consider one result from one of this paper. This construction of some spatial Lie algebra L, which is semidirect product of this Lie algebra, which is direct product of one-dimensional, direct sum of one-dimensional Lie group and three-dimensional compact Lie group, and n, where n is any nilpotent Lie algebra, and such that the bracket between z and SU2 is 0. If this bracket is not 0, and adjoint z is a positive multiple of the identity on each SU2 reducible subspace of n, then L admits an inner product with negative Ricci curvature. This result is interesting because we have some special construction where we use some very simple, yes, three-dimensional simple Lie algebra, and using some representation theory, we can construct very special inner product or matrix that have negative Ricci curvature. It's very interesting. And now we don't know how it could be generalized for more general situation when we have not three-dimensional Lie algebra, but maybe simple Lie algebra of any dimension. I don't know. This results is interesting because it's very recent and unusual. And in the recent paper, Laure and Weil found several families of non-solvable Lie groups admitting left invariant Riemannian matrix of negative Ricci curvature. And in recent survey by Laure and Weil, there is some overview of what is known on Lie group admitting a left invariant matrix of negative Ricci curvature, including many natural equations and conjectures in the solvable case, and so on and so on and so on. It's a very interesting survey, in fact. Now, in fact, we should mention some very important classes of some very important class of homogeneous space. Einstein homogeneous spaces. Recall that the metric G on the manifold M is called Einstein if the Ricci curvature of this metric satisfies the equation. Ricci curvature is multiple of metrics by some constant C. Of course, the theory of Einstein manifold, even in homogeneous setup, is very extensive and very developed branch of geometry. And of course, we should have more than one lecture to observe more or less even recent result on these topics. But the object of study is very interesting from different point of view because it's related to Ricci flows and so on and so on and so on. And we know that there are many interrelation with theoretical physics and some more or less interesting theory. Therefore, we have some, how to say, interest, some special interest to study this equation, to study homogeneous, remaining homogeneous spaces. And I want to finish this lecture only to show the special classic book by Arturo Lancelot Besset and more recent survey. This survey is survey by Mackenzie-1. It's very interesting from various point of view and related with Einstein homogeneous spaces, of course. And finally, thank you for your time and attention.